Okay, so we have so far seen the problem of flow past a circular cylinder. So this is a problem that we have done exactly, and the key results that we obtained was that when there is a steady irrotational flow past a circular cylinder, the drag will always be 0, and the lift would be non-zero if there was some circulation in the problem. So the question that we want to actually address right now, is this result specific to a circular cylinder, or it is applicable irrespective of what kind of an object do we have. So if I have steady translation of an object, so the body is translating, you could also have a flow past a body. So if you have a body that is translating, the body could be circular in shape, the body could be any other weird kind of a shape. The body need not necessarily be 2-dimensional, the body could also be 3-dimensional. So what would be the drag on the object? So I'll put u bar as the speed with which the body is actually moving. So going back to actually the problem that we have already solved, so which is the flow past a circular cylinder. So this is a flow velocity field that you are observing due to a cylinder that is held stationary in a uniform flow. The velocity field that you have given here in terms of r and theta, this is a velocity field you would observe if you were an observer sitting on the cylinder and there was a flow going from left to right. Now what would the flow look like if you were in the lab reference frame and the object was translating? See, the object was not stationary, the object was uniformly translating. How would you actually go about finding the velocity field? Now that's not too hard, right, because it's just a change of reference frame moving with constant velocity. So all you need to do is you need to subtract the uniform flow from this velocity that you have written down, and that gives you the velocity field that is generated by a moving cylinder, right. So if you say that I have done a change of reference frame, one reference frame which is basically translating with a velocity u infinity with respect to the other. So in this case, there is a velocity going from left to right with u infinity. So if you go to a reference frame which is basically now moving along with the uniform flow, then the uniform flow is basically there is no uniform flow, it is a stationary background and the cylinder is actually now moving. So when the cylinder moves, the velocity field that you are going to actually get due to this moving cylinder so for the circular cylinder, the velocity potential that we had was u infinity x plus lambda cosine theta by r. This was the velocity field that you, or the velocity potential that was due to a translating cylinder. Now if the cylinder was stationary, then this is applicable and you apply a boundary condition that ur is equal to 0 at r equals a, right. Now if the cylinder is actually moving, so this is the case of stationary cylinder in uniform flow, and the velocity field is u goes to u infinity x cap as r approaches infinity. Now if you do the problem where there is a translating cylinder in a quiescent fluid, so the fluid is at rest, no change happens to the equation. The equation still continues to remain del square phi is equal to 0. So once again, if I just write down my solution as u infinity x plus lambda cosine theta by r, what are the boundary conditions in the problem? At infinity, the velocity should go to 0. The fluid is at rest at infinity. I am trying to move an object. If I am trying to move an object, the object will be disturbing the fluid, and far away from the object the fluid is undisturbed. At infinite distance away from the object the fluid is undisturbed, which means the disturbance velocity should go to 0. That means that this part is actually going to be 0. There cannot be a uniform stream in my potential. The potential should only have the doublet part. Now, what is the boundary condition on the surface of the cylinder? Now, this goes back to the boundary condition that we are using. We are not using a boundary condition of 0 normal velocity. We are using a boundary condition of no penetration with respect to the boundary, which means the fluid velocity, its normal component. If you go back to your boundary condition discussion, the normal boundary condition is u of the body, if the body is moving with some speed. So, here I will assign a velocity which is u bar for the body, u bar dot n. So, on the surface of the body, the fluid velocity's normal component should be equal to the normal component of its motion. So, the fluid is, the particle is, or the body is trying to move with some velocity. The body has a velocity, it is a rigid body, it has a velocity u bar. So, at any point on the surface of the body, the velocity is always directed in this direction, right, it is always u bar everywhere, it is a rigid body. So, every point on the body is moving with the velocity u bar. So, the normal component at any point on the surface of the body is u bar dot n. Does that make sense? So, you draw n at any point and you can see that here it would be u bar cosine theta. At this particular location it goes to 0, there is no normal component of velocity at the angle theta equals to pi by 2, and similarly it would vary across the circumference of the body. So, the boundary condition that we arrive at is u dot n is equal to u bar dot n at r equals a. So, now if I write this down in terms, because u bar dot n, the body is moving in the x direction. So, this is going to be u bar cos theta, right. We have chosen the body to move, or we have decided that our x axis is along the line of motion of the body. So, the body is moving with a velocity u bar along the x axis. I have chosen my x axis that way, which means u bar dot n should just be u bar cosine theta. So, small u dot n, which is the disturbance velocity, if I am now going to actually calculate. So, I need to if you remember, small u dot n for a circular cylinder is my radial velocity, which is dou phi dou r. This is for a circular cylinder. So, for a circular cylinder, this is dou phi dou r. So, this at r equals a should be u bar cosine theta. So, what is phi? We have said phi is lambda cosine theta by r, which means dou phi dou r is minus lambda cosine theta by r square. Substitute, you will get minus lambda cosine theta by a square is u bar cosine theta, which means lambda is minus u bar a square. So, the velocity field now, which is basically given in terms of gradient of the potential. So, the potential is minus u bar a square cosine theta by r. So, when you write down the velocity field, it will have a radial component. The radial component of the velocity field would be plus u bar a square cosine theta by r square. this is in the radial direction, and then there is going to be an azimuthal component, and the azimuthal component of your velocity would be 1 by r dou phi dou theta, which is minus 1 by r square u bar a square. Dou phi dou theta would actually give me minus sin theta, right. So, I have a velocity u a square by r square just to make sure we have things done correctly. So, this is my velocity potential. I did a dou phi dou r, got a u bar a square cos theta by r square, and then u bar a square r square by sin theta theta cap. So, let us just go back and check what we had for the uniform flow. So, this was the velocity field that you got for the stationary sphere, stationary cylinder. So, u translating is equal to u infinity minus u stationary. That is basically the velocity field that you have. So, you only have the potential doublet as the velocity field in this particular problem now. Now, you have already seen what a potential doublet looks like. You are familiar with the velocity field due to a potential doublet. If you go back to the discussion of what a potential doublet looks like, the potential doublet right. So, if the sphere is or cylinders in this case is actually moving from left to right, it is going to push the fluid from its forward end and it will draw in the fluid from its rear end. So, this is what the instantaneous streamline pattern will look like for a translating cylinder. I use the word instantaneous because at the very next instant the cylinder is going to occupy some other location in space. So, if I draw the cylinder, you have to remember that the surface of a cylinder is no longer 0 UR. It is not that 0 radial velocity. The surface of the cylinder is satisfying the boundary condition that normal velocity of the fluid is equal to normal velocity due to its rigid body translation. So, the cylinder is translating with a velocity u bar. At a next instant in time, the cylinder is going to probably be somewhere here. Which means the streamline pattern is unsteady. You have a problem here where at every instant in time the streamline. So, if you were to do this as an experiment, you tow a cylinder, you tow a body in a fluid, you are going, if you take a snapshot of the streamline, this is what the streamline would look like at any given instant in time. But the streamline is a function of time. So, at the very next instant of time, the streamline would look different because it would have moved to a different location. And if you go back to what we did, which was flow past a stationary cylinder, there the velocity field was due to a uniform flow past a stationary cylinder, in which case the streamline pattern was steady. So, this is nothing surprising because you have done a change of reference frame, where now you are in the lab reference frame and the body is moving, and in the earlier problem you were sitting on the body and there was flow past the body. So, in the earlier case, because you were in the body fixed reference frame, the flow appeared steady to you. Now, in the lab reference frame, what you are going to observe is the unsteady flow field. This will not change the drag calculation, because we know the contribution from the uniform flow part of the potential does not have any part in the drag or the lift. So, this part is what could give you a drag, and this part continues to give you 0 drag even in this problem. So, there is no change in the scenario that you have. So, this is something which you have to keep in mind, that the streamline patterns look different for the same problem depending on what is your choice of reference frame. If you are trying to actually visualize flow past an irrotational flow past an object, you have to just make sure that you understand what you are trying to visualize. Are you doing it for a flow past an object, or are you doing a velocity field due to a moving object? Now, an interesting thing which you might have not paid a great deal of attention to is the fact that even if the cylinder was to move with a function of time, it was not moving with a constant velocity. The equation that we solve continues to remain the same. Del square phi is equal to 0 irrespective of whatever is the kind of motion that you execute, whatever is the shape of body that you have. So, del square phi equal to 0 with the boundary condition u dot n is equal to u bar dot n. Now, I am basically talking about a moving body. So, for any moving body moving with a velocity u bar, this is applicable, or this is the equations to solve irrespective of what is the kind of motion that you have. So, it is basically saying that imagine that there was a cylinder that was moving with velocity 5 meter per second. Instantaneously, by some means, you make it accelerate to 10 meter per second instantaneously. Even though you have managed to do this in a very short period of time, the potential that you have or the velocity field that you have will be immediately responding to the instantaneous boundary condition. So, what you have in potential flow is that the flow field responds to the instantaneous boundary condition. The boundary condition here is ut dot n, right. If you are saying the body is moving with some velocity which is a function of time, you can make the body do different things. So, take a circular cylinder, and if I plot u bar as a function of time. So, in one case it moves with 5 meter per second, and then gradually it approaches 10 meter per second. Now, you do another set of experiments where it is moving with 5 meter per second, and then it goes to 7, then it goes to 9, and then after a long time it goes to 10. The velocity field when both the cylinders are moving with 10 meter per second would be identical. The approach to that velocity or the history of that velocity is not there in the picture. And this is again something which will start to make you think that this is a bit unrealistic. This is a bit unrealistic because what you are saying that the adjustment of the fluid to any changes in boundary condition is instantaneous. And instantaneity is obviously an approximation, and this will basically motivate you in thinking that what is it that we are missing in the picture. And all of these things, whether we are talking about zero drag or whether we are talking about this instantaneous adjustment to the boundary condition, all of the questions have a common answer, which lies in the fact that we are ignoring effects of viscosity. So, gradually we are trying to actually build this to understand that what is it that we are missing out. So, if we now go back to what we just said about u bar of t. So, the question is the following: body of arbitrary shape moving with some velocity u bar of t. Now, clearly whatever we did for a circular cylinder, we used a lot of niceness of the polar coordinate geometry. So, what do? Let us say I am no longer interested in circular cylinder, I want to do a sphere. You will say, okay, fine, if I have a sphere, I will use a spherical polar coordinate. I'll say, okay, no, I don't want to do a sphere, I want to do an ellipse. You will say, okay, I'll go back and I'll find there is something called as an elliptical coordinate system. I'll do in that. Then you will say, okay, I will do it for a spheroid. So gradually after a point you will realize you are running out of number of special coordinate systems that you have to solve the problem. So we are not going to any longer stick to doing this for a specific dimension or specific kind of shape. We will invoke very general ideas to come out about the question that if I have a body, a rigid body moving in an unbounded fluid of any shape with a velocity u bar of t, if u bar of t was a constant, which means it was steady translation, what should be the drag? And if u bar of t was not a constant, how does that statement get changed? So that is basically what we will try to address. So our starting point is we are always solving a Laplace equation for velocity potential. So if you do Laplace equation in 2D, we saw that Laplace equation has a solution that is log of r. By writing it down in your cylindrical coordinate system, you see that log r is a solution of Laplace equation. Now if you do this in 3D, you will find that, so I will put a 2D here, I will put a 3D here, you will find that 1 over r is a solution of Laplace equation. So it will be 1 by r square dou r square dou phi dou r. So if you have 1 over r will be a solution of this. So this is basically known as the fundamental solution of Laplace equation in 2D and 3D. How does this help us? It helps us, you realize that if you have a solution, let's say, let's take the 3D one. So if you say 1 over r is a solution, you realize, so what you are saying here, 1 over r is a solution implies that dou square dou xk square of 1 over r is equal to 0. Right, that is the statement, that Laplacian of 1 over r is equal to 0. Now what about dou xi of 1 over r? Dou xi of 1 over r is basically grad of 1 over r. Is that a solution? So if I take a Laplacian of this, dou square dou xk square of dou xi of 1 over r, I can commute the derivatives, I will bring out the dou xi and I will have dou square dou xk square 1 over r, and what is this? 0, which means this also turns out 0. So in fact, if you know the fundamental solution of Laplace equation, then you can build solutions in this form. You can keep building solutions. So this is one decaying harmonic 1 by r, and you basically have a whole series of these decaying harmonics, because all of them are solution. You take Laplacian on any of these terms, it will be a solution. The Laplacian will commute with the gradients and eventually you will have a del square of 1 over r, which is a solution. Now we are interested in a solution of Laplace equation where the solution is a scalar, right? Phi is a scalar function. Now what is the order of this quantity 1 over r? In terms of tensor, what is the order of that quantity? 0. So this is a 0th order tensor. What is the order of del of 1 over r? It is a gradient of a scalar. So it would be 1. So it is a vector. This is gradient of 1 over r. It is a second order tensor. It is dou xi dou xj of 1 over r. So it is a second order tensor. This is a third order tensor. Now why are we saying all of this? Because this should be equated to a scalar on the left hand side. So I need to have a consistency of order. I cannot equate a vector to a scalar. So, we know that in general for a solution of a differential equation, when we write it down as a linear combination of all the solutions, there are constants. So, if you say that there is a differential equation involved of dependent variable y and independent variable x, then if y1 and y2 are the solutions, then the general solution is ay1 plus by2. So, here what you will do, you will say there is a scalar constant multiplying 1 over r, there is a vector constant multiplying the vector solution, because this is still a scalar. This is a constant, ai is a constant, but it is a constant which is a vector constant, it is not a scalar constant. So, ai dou xi of 1 over r. If you do the next one, it would be bij dou xi dou square dou xj of 1 over r, and this is how the series moves. Do not worry, I am not going to write down all the terms, we are just trying to see that how do we build solution without actually trying to solve the problem exactly for a particular problem. We are not going to solve this for a specific geometry, we are trying to keep it as general as possible, and you will get some very useful insight out of this. Now, when you do a problem of a body that is translating with some velocity, at this moment this could be translating with some arbitrary velocity. So, when you have this particular feature, what does this convey? What is that 1 over r potential? If you go back to what this was in 2D, so this is in 3D, right? In 2D, it would be a log r, then a vector constant dou xi of log r, then it would be bij dou xi dou xj of log r. What is dou xi of log r? Dou xi of log r would basically be dou r of log r dou xi, right? Dou r of log r we know, that is 1 over r, and what is dou r dou xi? That is the rate of change of your distance of a, so r is, what is r? R is the distance of any point, and r square is xk. So, dou r dou xi is xi by r, that is just the unit vector along the position vector. Xi by r is basically the unit vector that is pointing. So, xi is the position vector, you are trying to find out the rate of change of the position vector with respect to its length, and that is just its orientation, right? How do you write xi? Xi is basically going to be your position vector at any point whose length is r. So, if I am trying to find out what is the rate of that position vector with respect to its length, that is just going to be its orientation, which is xi by r. You can substitute, you can write r as square root of xk by xk and do a derivative with respect to xi, and you will get this answer. So, this is xi by r. So, I have xi by r square. What is xi by r if I were to use, let us say, circular polar coordinates? So, this is now in 2D, right? We are doing all of this now in 2D. I am trying to make you think in terms of 2D. So, what is xi by r in circular polar coordinates? It is cos theta. Cos theta, but obviously it is a vectorial quantity, right? So, it would be, it depends on that position. So, there will be a normal, and it would come in terms of ni by r. So, it would have a cos theta x cap plus sin theta y cap. So, now if you see in terms of this constant that you have the potential, so if you write down that potential, this is AI Ni by R, this particular potential. So, it is AI Ni by R. Now, what equation are you solving? You are solving a linear equation del square phi equal to 0, which is linear in boundary condition, which means the solutions should be linear in whatever is the forcing in the problem. You have a differential equation which is linear. The boundary conditions are linear. So, if I make the cylinder move with a velocity which is twice than its value, all the solutions of potential and velocity should increase by a factor of 2. We computed what was the potential for a cylinder that was moving with velocity u bar. If the cylinder now moves with a velocity 2 u bar, the potential will be twice that value, the velocity will be twice that value. So, what that says is that this AI should be Ui Ni C by R. It should be proportional to its velocity, that constant. So, Ui Ni, and what is Ui Ni? Ui is the direction of the motion of the body and N is the normal. So, it should be cosine theta into some constant by R. So, this is basically recovering that potential doublet from this piece. It is not obvious initially that that is basically a potential doublet, but now you can see that if this is a source, this is a potential dipole, because when you are taking a gradient of the source, you are going to get the potential dipole. So, in this particular form, it was not obvious that the dipole that we have been writing so far in this form as lambda cos theta. So, we have been writing it as lambda cos theta by R. This can be argued purely from tensorial point of view. You do not need to really solve this using solutions in polar coordinate or things of that sort. You can directly start off by saying that the solution that you have here would involve a gradient of log R dotted with something that is proportional to your velocity and a constant. So, that gives you the dipole solution. Yes.
There must be a ui term must be there, because the magnitude of ui will be there, right?
Where? Which term?
Ni ui.
Here, right? So, Ni ui bar, yeah. No, okay. Yeah, you are right. So, this constant, so this should be like something that is a constant, yeah, which will be having that thing. You are right. Now, our goal is, again, I am just rephrasing the point. Our goal is not to solve this exactly for any problem. We are trying to see how do you go about arguing this without really caring about the details of geometry and things like that. So, now you know this is a source. You are assigning physical meaning to these terms. This is a source or a sink term. This is a potential dipole term, and then the other ones are higher order singularities like quadrupole, etc. But we will just focus on these two right now. Now, if I have a solid object which is translating, can we have this term? Is it possible to have this term if I have any arbitrary solid object? We did not have a log R term in the cylinder problem, right? I gave you some very detailed argument that if you have the log R term, you will not be able to satisfy boundary condition, blah, blah, all those kind of things. But can we argue that without actually going into such great detail? So, phi is equal to a by r will give you a velocity which will be minus a by r square xi by r. The same approach, dodo r of r will base dodo xi of 1 by r will basically be dodo r of 1 by r into dou r dou xi. So, this is minus 1 by r square and this is xi by r. So, you have minus a xi by r cube. This is the velocity field that is generated by that 1 over r velocity. So, now consider, sorry, this should be a sphere. Consider a very large sphere enclosing this object. And you try to find out what is the mass flux through that region. So, you are trying to basically calculate, or rather just without the density itself, find the flow rate through that larger surface. So, let us call this surface as SR. So, I want to find what this is. So, what is u dot n on that surface? This should be minus a, r is capital R, xi is on this surface, xi is capital R ni. On a sphere of radius r, the position vector is the radius of the sphere times the unit normal to the sphere. So, this becomes r ni. What is the area element? R square d omega. So, r square r cube, all of these would cancel out. I had a u, sorry, I have, yeah, so then there is a ni here. So, u would have a ni and then there is an u dot n. So, that ni would become 1 and your answer would be minus 4 pi a. So, if I integrate this velocity over a surface of radius r enclosing the object, I get a volume flow rate that is minus 4 pi a. Now, what is the volume flow rate over the surface of the body? What is this? If I say the body is SP, what is this over the body? How much of mass is actually entering or exiting the body? 0. There is no mass that is entering or exiting the body. So, u dot n integrated over the body gives you the volume flow rate through the body surface, right, which is 0. There is no mass entering or leaving the body. So, this is basically going to be 0, which means this also should be 0, because what is the difference between these two terms? What is this quantity? If you apply divergence theorem, this quantity is divergence of u in the volume enclosed by SP and SR, right, which is 0, which means that if there is no volume flow rate through this surface, there cannot be any volume flow rate through the outer surface at any radius r, not possible, which means that this should be 0 and that means that there cannot be a source term. You do not need to know what is the shape of the body. You do not need to know how fast or how slow is it moving. As long as the body is a rigid solid surface, there is no motion, there is no flow through the body, you will not have the source term. So, finally, what we are concluding here is that the potential that is going to be driven by a translating object will take this particular form, ai dou dou xi of 1 over r. There can be other terms, but at large distances from the body, this is what the potential will have. It does not matter what you have as the shape, because the shape is going to be captured by this constant. That constant will have information regarding the shape of the body. And what we will do next is we will see that using this particular form of the potential. So, we have arrived at a very general solution of a translating body. If you want to make this more specific, because we are now saying that there should be a linearity with respect to the motion of the body, right. I have some arbitrary shape boulder that is moving. It is moving with a velocity u of t. So, the entire solution, because I am solving Laplace equation, which is a linear equation with linear boundary condition, the entire solution that I will obtain ui should be some constant, some scalar constant times ui. Okay. So, we can write this now. In this particular form. So, you realize the calculation takes a very generic or very simple form without even knowing a lot of detail regarding what is going on in the particular problem. So, with this, so what we will write out is that your potential can be written as a product of your translation and this vector potential, which is dou xi 1 over r in this case. Obviously, it does not stop at dou xi 1 over r, there can be other terms, but I am just giving you the feel for what this term is. There can be other terms in the problem, but all those other terms far away are going to decay. So, this term is decaying as, what is the decay of this term? It is a gradient of 1 over r, so it decays as 1 over r square. So, the dipole in 2D decays as 1 over r, in 3D it decays as 1 over r square. So, whatever term I am ignoring here, those terms are going to be higher order, because that is going to be gradient, additional gradient. So, we will keep it at this and try to work out what would be the force on the body. And once we have the expression of the force, we will actually try to conclude regarding the drag. And I am leaving at one simple point here, that now that we have an idea of this potential, what would be the momentum for this problem? So, you said the potential is going to go as 1 over r square far away. The velocity potential decays as 1 over r square, which means the velocity will decay as, velocity is a gradient of potential, right. So, it will decay as 1 over r cube. So, now in this integral, the integrand goes as 1 over r cube. How does dv go with r? dv will go as r square dr and the angle, right, which means this is an integral which is dr by r. So, it is a bit of a mess. It is a bit of a mess in a sense that depends on how you have defined, your outer region, outer boundary. This integral can become, so what is dr by r? Log r. So, you can get a divergent answer, it depends on how you have defined your domain. So, this quantity, the momentum for the problem, when you have a translating body in irrotational flow, the momentum is something that cannot be defined, and which is a bit of a puzzle, because if you are not able to define momentum, how the hell do we define something like a drag, which is rate of change of momentum? So, we will think a little bit about this, and this will take us to our idea of a concept called added mass. So, you cannot define momentum of the fluid for a translating object in inviscid flow, because the velocity field, the way it decays, the momentum is going to be undefined. You can see this very clearly. You do not need to know the shape, you do not need to solve the full problem. You know that velocity cannot decay faster than 1 over r cube far away from the body. which means rho u dv will be an undefined integral, which is the momentum contained by the fluid. So, as the body tries to move, there is no meaning to defining the total momentum. So, what we will rather try to look at is that if there is a slight change in the velocity of the body, how much would the momentum change? So, the change in momentum is what we are trying to calculate based on the energy. So, this is something which we will do in next class.